So we have the notes for section 7.2, which deals with anti-differentiation by substitution. So we start with discussing indefinite integrals. So the family of all antiderivatives of the function f of x is the indefinite integral of f with respect to x, and denoted by antiderivative or integral of f of x dx. So if capital F is any function so that the derivative of capital F is equal to f of x, then the antiderivative, or the integral of f of x dx, is equal to cap of f of x plus c, where c is an arbitrary constant called the constant. So this is a constant of integration. So once again, this c shows up because you're not sure what number was hanging out at the end. If you remember, if you talk about, if you take the antiderivative of, let's say we'll call it 2x to make my math easier. This is x squared plus c, because these equations, x squared plus 1, x squared plus 2, x squared minus 1, like they all have the same derivative. So you don't know, without having some points to work with, what that value of c was, because x squared plus 1 has a derivative of 2x. X squared plus 2 has a derivative of 2x. So when you do the antiderivative, you don't know which one of these potential things you got, and unfortunately, there's an infinite number of them. You could be x squared plus 1.1 repeating. So that's why that plus c shows up. All right, so evaluate the integral of x squared minus sine x, so the antiderivative. So for powers, exponents count up by 1, and then the reciprocal goes out front. So the antiderivative of x squared is 1/3 x cubed. The antiderivative of negative sine is actually positive cosine, and I just need to put a plus c on the end to take care of that constant of integration. Okay, so we got a big table, properties of the integrals. So first one is just constants. So if you can factor something out, you can take it out front and not have to worry about it when you do your antiderivative. If you have multiple terms inside, you can separate them into separate integrals. Power function rules, this is the one I just used, so you count up the exponent, n plus 1, and 1 over n plus 1 is essentially the reciprocal of the exponent, as long as n is not equal to negative 1. Because if that is the case, you have to use this rule. The antiderivative of something to the negative first is the same thing as 1 over that, which is the natural log. Notice that there are absolute values here, because you cannot take the natural log of a negative number. Here's your trig identities. So the antiderivative of cosine is the sine, secant squared is tangent, so on and so forth. If you notice, if you read these from right to left, the derivative of sine is cosine, the derivative of tangent is secant squared, so on and so forth. Then down here we have our rules for exponentials. So the antiderivative of e to the u is e to the u, because the derivative of e to the u is e to the u. The antiderivative of the natural log ends up being this string. Log base a ends up being this string, and a to the u ends up being this. So we'll probably be using these rules later on. Okay, so which brings us to the Leibniz notation and the antiderivative. So, example, let f of x equals x cubed plus 1 and let u equal x squared. Find each of the following antiderivatives in terms of x. So f of x dx would be the antiderivative of x cubed plus 1 dx. So this would be 1/4 x to the 4th plus x plus c, or x to the 4th over 4. So here, f of u, so this is, let's see here, f of u is this equation, u cubed plus 1 du. So because it's just the f of x equation with u instead of x. So this would be 1/4 u to the 4th plus u plus c. But since it says in terms of x, I need to replace these x's, or sorry, these u's with x squareds. So this becomes 1/4 x squared to the 4th plus x squared plus c. So 1/4 x to the 8th plus x squared plus c. Now this last one, f of u dx, means that I have to do my substitution before I do the antiderivative, because I need x's before I antiderivative. So this would be antiderivative of u cubed plus 1 dx would be the antiderivative of x squared cubed plus 1 dx. So the antiderivative of x to the 6th plus 1, which would be 1/7 x to the 7th plus x plus c. So you have to be careful. This variable at the end tells you what the variable you should be looking for here is. So you can't do f of u dx because that's not the right variable. I need to substitute my x's already. Okay, So substitution in indefinite integrals. So we got evaluate the sine of x, e to the cosine x. So let's make our u, we'll call it the exponent here, cosine x. So du is the negative sine x dx. Let's see a better way to explain this. Yeah, so, well, here, we'll look at it this way. So the derivative is du over dx, but I need to get dx by itself because of this dx term at the end. So what would happen is this would become du equals negative sine x dx. So dx is equal to du over negative sine x, and then I'm going to make a substitution. So the antiderivative of the sine of x, e to the u, but instead of dx, I have this stuff, du over negative sine x. Now if you look, these guys cancel, so I actually have, and there's still a negative, so I have the negative antiderivative of e to the u du, which just becomes negative e to the u, because the antiderivative of e to the u itself, and then I undo my substitution, so negative e to the cosine x. So for this guy, we'll make our u the stuff underneath the square root. So it'll look like this. So du over dx is the derivative of this, which is x to the sixth. Oh, sorry, 6x squared. So du is equal to 6x squared dx. So dx is equal to du over 6x squared. And we do our substitutions. So x squared, square root u, times du over 6x squared. So x squared can cancel. So I actually have, there's a 6 on the bottom here, so let's say 1/6. We'll make this a power. So we have this guy, 1/6 u to the 1/2. So 1/6. So if I count up the exponent, that's 3/2. The reciprocal goes out front. Oops, I forgot up here, I forgot my plus c since I have an indefinite integral. So this would become, let's see here, so that can cancel that, make it a 3. So that's 1/9 u to the 3/2 plus c, and then return it back to x's, 5 plus 2x cubed to the 3/2 plus c. And that's our final answer. All right, number 5. This one, okay. Now, cotangent does have a little bit of a trick. This also happens for tangent. The cotangent of 7x is equal to the cosine of 7x over the sine of 7x. So I'm going to make my u the bottom of the fraction. So du, I'm going to start skipping steps. So the derivative of this is 7 cosine 7x dx, which means that du over 7 cosine 7x is equal to dx. And then we do our substitutions. So let's see how to write this. So I'll write it with my, so that's using this substitution. So if u is sine 7x, so this is the antiderivative of the cosine of 7x over u times 1 over 7 cosine 7x, or sorry, du over. So the cosine 7x can cancel. I have a 1/7 I can pull out front, 1 over u du. So the antiderivative of 1 over u is the natural log of the absolute value of u, and then undo your substitution, which was u is sine x, or sine 7x. So there you go. All right, so 6, find the indefinite integrals. In each case, you can use a trig identity to kind of, so similar to what we did up here, to set up a substitution. So let's see here. Well, So we'll make this guy, instead of 1 over cosine, the secant squared. So this guy is kind of our inside thing. I'm not using secant because I know what the antiderivative of secant squared is. So my u is going to be 2x. So my du is 2 dx, which means dx is equal to du over 2, or half du. So do your substitution, the secant squared of u times du over 2. So over 2 is the same thing as having a half. So I've got this expression. Well, the antiderivative of the secant squared is the tangent, and then undo your substitution. Oops, not plus c. Now, always you can check, if you take the derivative of this, you'll get that. So this is technically, derivative of tangent is secant squared, derivative of 2x is 2, so you have 1/2 secant squared 2x times 2, halves cancel. Cotangent squared, let's see here. What do we want to do with this guy? Nope, I know what we need to do. We need to use a Pythagorean identity. So this is the same thing as the cosecant squared of 3x minus 1 dx. So my u is going to be, because I know the antiderivative of the cosecant, it's the cotangent, or cosecant squared, so we're going to use that. So du equals 3 dx. So let's see here, du over 3 is equal to dx. So do your substitution, cosecant squared of u times du over 3. So that's 1/3 cosecant squared u du. So the antiderivative of the cosecant squared is the negative cotangent squared. So 1/3 times negative cotangent, or no, just negative cotangent u plus c. Undo your substitution. And then you have cotangent 3x minus 1 plus c. And there you go. Nope, no, I lost something. Did I? Oh, yeah, I did. There should be a minus 1 here. That it's just the 3x's inside the cosecant. So that's a minus 1, which means there's a minus 1, which means there should be a, minus 1 there. So we would get a, so you would have 1/3 times negative cotangent u minus u plus c, which would become negative 1/3 cotangent u cotangent 3x minus 3x plus c. I knew that one went away somewhere. Okay, cosine cubed. So let's see here. So we're going to turn this guy into cosine squared x times the cosine of x. And then we're going to turn that into 1 minus sine squared x, cosine x. So my u is going to be the sine. So du is equal to the cosine of x. So du over the cosine of x is equal to dx. So do your substitution. So this becomes 1 minus u squared cosine x times du over cosine x. So those cancel. So I have 1 minus u squared du. So this would be u minus 1/3 u cubed plus c. And then undo your substitution. The sine of x minus 1/3 the sine cubed of x plus c. Typically, you need to write it in terms so that you have something and its own derivative. So I wanted this to be in terms of sine because the cosine is the derivative of sine. Up here, I needed something that I knew the derivative of, so I had to use a Pythagorean identity. Okay. So, substitution in definites, you can do similar things here. Let's evaluate from 0 to pi of the tangent x secant squared x. So let's say our u value, so secant squared is the derivative, so u is going to be the tangent of x. So du is the secant squared x dx. Now if you notice, like right here, that matches exactly that. So I can just replace, I don't need to necessarily solve this for dx and substitute and cancel, as long as I get an exact match. You can just do the straight replacement, but if you don't see it, so du over secant squared x equals dx. So do your substitution. So tangent, nope, that's u, because tangent's u, times secant squared x times du over secant squared x. So we get this. Now if you notice I left the bounds off, and that's because if I change my variable, I have to change my bounds. These are in terms of x. I need them in terms of u. So if x is 0, to figure out what the lower bound is, I plug 0 in for x. So u is equal to tangent of 0, which is 0. At pi over 3, the tangent of pi over 3 is root 3. So these are my new bounds. So this becomes from 0 to root 3, secant squares cancel, of u du, which is 1/2 u squared, evaluated from 0 to root 3. Notice there's no plus c because I have a definite integral. I can actually do the calculations in this case. So it's f of a minus f of b, so it's 1/2 root 3 squared minus 1/2 0 squared. So let's see here. So this is root 3 halves minus 0, so the whole answer is just 3 halves. Okay, so we've got this guy. So when you see a fraction, typically your substitution is going to be the bottom of the fraction. So du is equal to 2x dx. So solve for dx, so du over 2x is equal to dx. So let's see here. So the bottom is my u. So I've got x on top still, du over 2x. So to fix my bounds, if I plug 0 in here, I get -4. If I plug 1 in, I get -3. So those are my bounds in terms of u. So the x's cancel. There's a 2 on the bottom. That's the same thing as having a half. So I have this. So the antiderivative of 1 over u is the natural log of the absolute value of u, all evaluated from -4 to -3. So doing this, this would be 1/2 ln 3 minus 1/2 ln 4. So granted that's 1/2 times the natural log of 3 minus the natural log of 4, because factor. A property of logarithm says if you have a difference, you can actually rewrite it as quotient. So 1/2 the natural log of 3/4 is the final answer. And that brings us to the end of the section.